Continue our session, and here at the talk of Nies about classical notion of Demuth randomness.
Martin-Löf randomness is often considered as a notion that's too weak. It allows for the set or real to be Turing complete. Right? Something that's random shouldn't be able to compute a halting problem. So omega is only the number of wisdom because it's not really random. Also, the recent research on almost everywhere theorems in analysis sometimes, not always, often shows Martin-Löf randomness is too weak, because here you want effective versions of these almost everywhere theorems, such as Lebesgue density. Right? Martin-Löf randomness doesn't imply density 1 for maybe the most natural effective class, namely effectively closed sets. So here's the definition of density. We'll get back to this quite often. So I put it right here and also there. So you have a subset of the unit interval. You want to know how much of the real is in that set as you zoom in on the real. And the lower density measures just that. It measures how much is in the set around the real, as if you divide by the length of the interval that you consider. So it's the limit of that. The famous Lebesgue density theorem says for almost every point in the unit interval that is in E, the density is 1, in fact. People have proposed strengthenings of Martin-Löf to address these two problems. Right? So, okay, if Martin-Löf was too weak, just relativize it to the halting problem. Right? Why not? So that's two randomness. Two randomness means Martin-Löf random relative to 0 prime, the halting problem. So such a thing is random in 0 prime and therefore doesn't compute 0 prime, of course. And also if you write down what it means to have density 1, it's easily seen that any 2 random has density 1. Right? In fact, weak 2 random is enough. So if you fix epsilon and say the density is less than 1 minus epsilon, that's a pi02 null class. That's a weak 2 test. So 2 randoms certainly do it. The problem is this was too much already, right? 2 randomness has widely overshot the goal because we still want to keep the nice interaction with computability and also computable analysis that Martin-Löf randomness provides, right? Omega is good for that reason, but we want somewhere in between, right? So 2 randomness is too strong already. You lose that interaction. For instance, if you have a 2 random, there aren't any interesting, easily described sets below, right? Unless they are computable. So any delta 2 set below a 2 random is computable. So here's a collection of notions that are supposed to address this Demuth randomness and its variance, which are actually weaker in this talk. So Demuth implies weak Demuth, implies something called balanced random, which implies difference random of Selvin and Johanna Franklin. And all these implies Martin-Löf random. So the weakest notion I have here, which is difference random, still implies Turing incompleteness. It's actually equivalent to Turing incomplete for Martin-Löf randoms. And the next one, balanced implies density 1 on effectively closed classes. So how about Demuth itself? The strongest notion I have here still is compatible with things you want to do in computability theory, right? In fact, the Demuth random can be delta 02. So it's still not so strong to forbid this interaction. So that seems to be the right compromise, one of those notions. So the two things we'll observe will be these notions are actually very useful for computable analysis, and that was Demuth's original motivation, constructive analysis. So we get effective versions of AE theorems such as Lebesgue density and Denjoy-Zhang-Sachs theorem. And another, for me, exciting development is that since these notions still interact with computability, you can use them to solve problems that people working on this interaction of randomness and computability were interested in, such as the K-trivials. Right? So anti-random, which is the same as very low, these properties can be analyzed using Demuth and its variants, and in fact can be used to solve open problems there. All right, so the plan is to first introduce Demuth randomness, some properties, then I tell you about the interaction with analysis, and finally some more results about Demuth randomness and lowness. Because for the interaction with analysis, we'll see that that notion is actually too strong. So this is Demuth. Thank Ton Kuchera for providing these pictures here. So he lived from 36 to 88 and worked all his life at Charles University in Prague, studied in Moscow under Markov with a PhD in '64 in the Russian School of Constructive Analysis. Right, so let's try to get the definition of Demuth randomness. Right. So the idea is you have a Martin-Löf test and the components, which are sigma 1 sets, so they grow just like that, but you can actually exchange the whole components, replace them by something different. Right. So the whole sigma 1 class, or its description rather, can be replaced for a computably bounded number of times. You can start thinking why a constructivist would like these notions, right? So failing a Demuth test means for infinitely many n, the real is out of the final version of that component. So passing means for almost all m it gets it, right? These things can be not nested, so they're not necessarily decreasing. So it's a strong passing condition, right? What Demuth actually defined was non-randomness. As a constructivist, I don't think random things existed for him, in fact. So he would say he studied effective null sets or something, right? So he defined definitely non-randomness, and what he called these things is WAP, which is weakly approximable in measure. So that seems constructive also. Yeah, I'll get to the formal definition, but it means just say, oh, this component wasn't good. After a while, you say, here's a different version, a different sigma 1 set, which I want as the m's component. And now you have to be out of that one. So replace it by something else.
And also not for all m, for infinitely many.
Yeah, failing to for infinitely many m, it's so to be random has to really be good in that it's out of almost all of them. Okay. So this is the actual definition in constructive this notation, and it's fun to try to get through. Right? So first you notice there aren't any sets really, it's all numbers, right? They're only indices. It all defines predicates of natural numbers, like this stuff, right? But you can actually find your way through and see that what's happening here is exactly what the current interpretation is, right? So Q is an index and K is the case component, and it says the limit of what you compute with that index has measure at most 2 to the minus k minus 1. This p here is a computable index which gives you the number of mistakes here. This is the number of mistakes. And it says the number of mistakes that changes is at most p of k. Okay, the Russian doesn't have much, but there's much in it anyway. And you can see here, this is a Demuth test, right? It says for all m there exists n greater than m, so that, well, you meet this condition, right? So there's infinitely many m's where you are in. Right? And the other quantifier order is weak Demuth randomness, I'll get to in a bit. Right? Of course, you also need double negations when you define the absolute classes, which is what you can see here. All right, so maybe it's better to give the actual formal definition of both notions, weak and full Demuth randomness, which I also have here. So you have, I guess, 45 minutes or so to read it. It's a bit ugly, but the notion is not there for its definitional beauty, but for its usefulness. Right? So WE is interpreted as a subset of the strings, binary strings, and the open set given by that is denoted by this symbol here. And now the Demuth test is a sequence of sigma 1 classes, Sm. And now the computably bounded number of changes is given by what I call omega computably approximable function, right? Also omega CE, or same as weak truth table below 0 prime. These things are all the same. There's some movement to call these CA, not CE, but hopefully people won't notice too much. So omega CA then means the number of changes of that function is computably bounded, right? And the Demuth test is given as a sequence of sigma 1 sets where the mth component is computed by an omega CA function. Right? And implicitly that means we have the changes, right? Because that function changes a computably bounded number of times. So at each stage we have a version, which is the value the function gives us at this stage. So that's the version of Sm at stage t. Questions on this, which is the main notion. So passing, as I said, means out of almost all. And if the test is decreasing or monotone, then passing is easier. It's the same as being out of some, right? So if you pass only those tests, you call it weakly Demuth random. So it's really this idea of changing the component that's so important, right? There's many variants, but the idea of changing is very important because you want to say, okay, Turing complete isn't possible, but how can we get close to Turing complete and be random? Right? So and that can be formalized in many successful ways by changing components.
So for example, any monotone, any limit lower semi-computable real is not.
Yeah, any.
You can just change the interval.
Right. Omega, even if the bit sequence is omega CA, that's weaker. It's still not Demuth random, and in fact not even weakly Demuth random, because the component up to at stage m, sorry, the component m at stage t is just what the set gives us at stage t. The first m bits at stage t, the open set corresponding to that. So here's some randomness notions in context. I said too random is the obvious generalization, but too strong. There's a class called limit random, which is the same as Schnorr random relative to 0 prime. So that's the one where the number of changes is not bounded at all, just a finite number of changes, otherwise the same definition. This kind of thing is not acceptable for constructivists, right? So these things don't exist for Demuth, right? And here it splits apart. This side exists for Demuth, this doesn't, right? Weakly to random means the measure goes to 0 of the generalized test in some way, right? But not effectively bounded. If you pass these tests, then you are weakly to random. This is kind of philosophically interesting that these two are incomparable. This is the classic notion, this is the constructive notion. Right? It's the ones where you have incomparability. Right? So these merge again at weakly to random, weakly Demuth random, right? Which is the passing condition that you only pass monotone tests. And there's a few more in between, and these imply all margin left random, right? So let's study a few properties. So existence and some limitations. As I said, Demuth himself proved there's a delta 2 Demuth random set. And another result says these sets are actually Turing incomplete, and in fact much more, they are GL1, generalized low 1. And even better, you can sort of bound the size of the jump for these sets. So if Jz is the jump function applied to Z, you can more or less easily show that there's a omega ECA function at bound 2 to the n that bounds the value, right? So it only goes up 2 to the n times and will bound the value. This implies GL1 immediately. So this isn't true for weak Demuth, and in fact, when the proof doesn't work, the fact isn't true. We'll see that in a moment. First, these Demuth random sets are not computably dominated, which computably dominated would mean there's a single, each function the set computes is dominated by a computable function. Right? So Joe Miller, who sadly isn't here, or is he? No, and I proved some time ago, if you are computably dominated in GL1, then you are not diagonally non-computable, in particular not margin left random. So this, of course, since the Demuth randoms are GL1, means that they cannot be computably dominated. The functions they compute actually grow more or less fast. A weakly 2 random can be computably dominated. This result strengthens the effect of Kurtz, I guess, that 2 randoms are not computably dominated. Okay, so that's some basic property. So here's a result of Tonda Kuchera and mine. A weakly 2 random can be delta 2 and high. Right? We have a weakly 2 random, a weakly Demuth random here. It's there. Right? High means 0 double is Turing below Z prime. Super high is a stronger notion where the reduction is actually TT. Right? So 2 random can still be high, but it cannot be delta 2, of course. So this is something in the context of delta 2. A fully Demuth random cannot be high because it's GL1, right? So if it's delta 2, it would be low. So that separates the two notions. The Demuth randoms sit in delta 2 sit down maybe here in low. So the strong passing condition is actually very important. So again, there's a delta 2 weakly Demuth random that's high, and another result is it cannot be super high. Right? So that's where it splits off. So I'm surveying the results that have happened on this notion in the past couple of years. I mean, long after Demuth. The notion is just 30 years old this year. So there's a characterization by initial segments similar to Levin-Schnorr. It's of course a bit more complicated. In fact, it's a bit like a weakening of the initial segment characterization of two randomness, right? So here we proved that Z is two random just if for some B or infinitely often the C complexity is maximal for B. So this is the result on characterizing two random by initial segment complexity. Hölzel, Krelling, Stefan, and Wu have proved that Z is Demuth random if, well, quite a bit of a mouthful. This thing happens here. So for each omega CA function, for almost every B, there's some n greater than f of b where you have incompressibility for n minus b. So f grows really fast, and it tells you still get incompressible initial segments high up. Right. I think it's right. Yeah, so it's a weakening of the two randomness thing. Right. And that proved I did other useful things. For instance, in the definition of Demuth test, you can assume the versions are Clopen, right? Fully given as by finite sets, Clopen sets given in all detail. And you cannot do this for monotone tests. It's impossible. Right? So this has been useful in later papers, such as this one here. So the lowness notion for both Demuth and weak Demuth are known nowadays. So what does low mean in general? So if you have a randomness notion C, low for that randomness notion means the oracle doesn't get you better tests in that sense, right? The power of the oracle doesn't add to the strength of tests, or formally every C random is already C random relative to A. So this is a quite indirect definition. So people want to characterize it by combinatorial or plain recursion theoretic conditions. That happens a lot, but it's often hard to do and unexpected. For instance, low for Martin-Löf random is the same as K-trivial. So there was an initial result by Downey and Ng showing that the low for Demuth randoms are all computably dominated. So the oracles now, not the sets themselves. Don't confuse that. It's an oracle. It doesn't have to be random itself in any way, right? So that was an initial result, and there's a characterization saying that low for Demuth and low for Demuth tests, which means slightly stronger, is the same as being computably dominated and Demuth traceable. Something we call Demuth traceable, which is, well, it's also not very easy to define. Obviously, the characterizations should reflect the tests in some way, right? They reflect the test concepts it's built out. But I think I can explain it with this idea of computably bounded many change it, right? Steve Simpson here had a definition of omega CA by A functions, right? Which sort of was one of the first results in this what we call now partial relativization, right? So you take a notion, a complex notion, but you only relativize parts of it. In this case, here you relativize G to A, but you still say the number of changes is computably bounded. Not A computably bounded, just actually computably bounded. So you want to find traces for these functions. A trace is an array of finite sets catching the value. In this case, you want omega CA trace, not mentioning A, of course, where the size is fixed, say 2 to the x for gx. Omega CA means you can exchange the index for this set a computably bounded number of times, and therefore the set itself. Right? So that's the notion of Demuth traceable. We also built a perfect Pi-0 class of Demuth traceables. Right? The question was actually, is there a low for Demuth random outside computable? Answer yes, there's perfectly many, in fact. Because Martin Miller now applies and shows there's a perfect subclass of computably dominated things, right? So which by this conjunction here must now be low for Demuth tests, in fact, and therefore low for Demuth random. Right? So that's the lowness. This is interesting because the kind of lowest class of this kind before was computably traceable, which is low for Schnorr, right? It's interesting, it makes a connection of Schnorr randomness to Demuth, and also it gives an interesting subclass here of the low for Schnorr things. Because the Demuth traceables are all jump traceable, and then these inclusions hold. They're all proper. So that's a recent paper submitted, and we also showed that low for weak Demuth is just computable. Don't ask me why. I mean, it always seems technical, right? It's the, for instance, that you can use Clopen tests is important, which isn't true for weak Demuth, right? And so on. So that's the definition and basic properties on Demuth. Now I go on to analysis. Any questions so far? Give you a moment.
Complicated in the arithmetical hierarchy is the class of low for Demuth reals.
Would we calculate that?
It's arithmetical, but
where exactly pi something, pi 4 maybe? Has to be calculated. But
I want it to be pi 3.
Oh yeah, I know why. Oh. Yeah, to check the definition. Can't tell you right away. Any other? You all understand the definition?
all right, so let's see Demuth's original motivation and what grew out of it later with regards to Lebesgue density. So I told you he came out of the Moscow constructive school where everything's computable, right? And Markov computable was maybe the most natural definition of computable function on the unit interval for these researchers, right? So Markov computable means you take an index for a real, or rather a Cauchy name, a computable Cauchy name by an index for a real, and you can computably map it to the image of the function, also given by a index for a Cauchy name. So everything is on computable indices. Cauchy name means the Cauchy sequence that converges where the nth member is at most 2 to the minus n away, so converges fast. So these functions are more inclusive than the usual computable, right? But they are continuous on computable reals, and nice things happen. Right? So it's not that easy to find a distinction between the plain computable functions and this more general class, right? So Demuth knew the Danjois theorem, but he called it Garg's theorem for some reason, some rather obscure publication. So he was interested whether the Danjois alternative holds at the real, right? So Danjois alternative means either it's differentiable or highly non-differentiable in the sense that the upper and lower derivatives are plus and minus infinity respectively. Young-Sachs says for any function this is true for almost every real. Surprisingly, no restrictions on a function. Given a function is partial, possibly you need to be a bit careful how you define the derivatives. So you only take things where it's defined. Rationals would suffice, actually. So he proved for any Demuth random real this alternative holds for any Markov computable functions, and realized that Martin-Löf randomness is not enough to do this, right? So he made an example of a Markov computable functions where the Dangeroux alternative fails at a, well, something he would call Martin-Lev random real, and whatever that meant for him. Right? So Martin-Lev randomness is not enough. Right? This may have been his motivation to introduce that notion. Some constructive strengthening which makes the Dangeroux alternative hold. So now I start a different notion, difference randomness, much closer to Martin-Lev, but strengthens it slightly. So what you do is take a Martin-Lev test and replace the components by differences of open sets, all effectively given, same measure condition. You can actually fix the second component. So you just say I intersect all of them with a fixed Pising 1 class. That's the same thing. Right? So if you pass all these tests, then you're called difference random. Franklin and showed for Martin-Lev random, difference random is the same as, the pattern is not above omega. Yeah. So this means not. Turing incomplete. Can't fix that. Omega is Turing equivalent to 0 prime. So you can view it as a further weakening of weak Demuth randomness, right? So you have weak Demuth was these monotonic tests, and now you also say each time I start a new version, it has to be disjoint from the previous versions, right? That's called version disjoint. So formally, remember this was the version at stage T1. If they're different, meaning actually as indices are different, then they're disjoint, right? And it's not hard to say that. No, I did right. If omega is Turing below z, then that is not difference random, right? It's maybe the nicest of these implications, right? Say omega is gamma z, you have a Turing functional gamma computing omega, right? Miller-Hughes says we can assume these oracles computing omega up to n have measured at most 2 to the minus n plus c. The possible oracles computing initial segments shrink quickly, right? Using that z is random, of course. Right? So then we have our versions right away. We just say, okay, at stage t, take all the oracles that compute omega t up to n plus c. Right? This stuff. And that's of course version disjoint. If omega moves, you have a different oracles. They compute something else. Right? So once you know version disjoint is the same as difference tests, this is some more implications you can prove this one easily. You see how these moving components come about, right? It's a nice example. And in fact, they are version disjoint here. So why do I tell you about difference randomness? Well, this is the notion we used in a recent paper here to show that, well, Demuth was right, but his notion was way too strong, in fact. Right? I was sitting there last year in Paris, and we were thinking, why does he come up with this strange changing condition with computably many changes? What's that have to do with differentiability? And in fact, it doesn't. Right? I mean, it's really difference randomness is enough. I'm not sure what his proof was like, but we have a proof not using any changes beyond the ones that are in difference random, right? So here's the classic theorem again of Denjoy-Jong-Sachs. And the standard proof uses a concept that's only slightly obscure in analysis, the concept of porosity, right? Meaning having holes around a point close by, right? It's like a sponge, right? So say P is a subclass of the unit interval is porous at a real Z if for some epsilon there exists arbitrarily small alpha, so that around the real, the interval given by alpha, you have a hole of size epsilon alpha. There's a hole around Z as you move in on Z. The hole has a fixed proportion to the interval it's taken in. Right? So if you look at Bogachev's, for instance, proof, at an important point, porosity comes in. Right? Because this works by using Lebesgue theorem that a non-decreasing function is differentiable almost everywhere and reduces it to this case. And somewhere to make this transition, you need porosity, right? And in fact, rather that the real is not porous, that P is not porous at the real. You don't want holes, right? So that's what's a crucial lemma. If P is effectively closed and Z is difference random, then P is not porous at Z. So that was needed for the effectivization, along with many other things, to get the full result that difference random is enough. And now this is our chance to get back to Henri Lebesgue, right? Because porous is obviously closely related to density. If P is porous at Z via epsilon, then the density, remember here, this definition, the density is at most 1 minus epsilon, right, because of these holes. And so in particular, it doesn't have density 1 at Z. Right? And now I want to replace porosity by the much better known concept of density, and digress for a moment till I get back to the concept of changes of test components, which is intimately connected to this. Okay. So here's the theorem by Lebesgue. It's actually not stated as a theorem, it's this. Can anybody read this for us? No,
so having the same reasoning on the
no, in French, please, in French.
What?
I want to hear it in French.
How is that helping anyone? Most people. Raisonnant de même sur la densité à gauche, on voit finalement que la densité d'un ensemble mesurable est égale à 1 en presque tous les points de cet ensemble.
Great. That's just because I have the translation here.
Oh.
Yeah, it's actually the end of a proof, and then it's stated at the end as some statement.
You see that Lebesgue didn't have tech yet.
Yeah, typewriter. Thanks a lot, Laurent. So here's the translation, which I mentioned already, and it's very important. Theorem, obviously. So what's the connection to randomness in effective versions? We want to know that. So I connect it again to difference randomness, but technically I don't get full density 1, I only get positive density, for now at least. So positive density means just this, what you would expect, rho is never 0, right? So rho is positive. The lim inf is positive. So we say Z is a positive density point if this holds for any effectively closed set containing Z. Right? So it's a universal quantification over effectively closed sets. And now this is exactly what we need. I mean, Turing incomplete is exactly what we need to get positive density for Martin-Löf random. So these two are equivalent. Z for Martin-Löf random Z is not above the Hotting problem just if Z is a positive density point. Right? So in the analytic characterization of Turing incompleteness within the randoms, the proof is interesting because it doesn't actually take Turing, it takes the analytic definitions and converts one into the other. So if you fail a difference test, meaning you are in an effectively closed set and also in a descending sequence of sigma 1 sets in the right way, then you can make a hole in the same effectively closed set. So this was used to solve a long-standing open question this question was solved by Day and Miller. The question on the K-trivials, here's the definition. Hope you've seen it. K-trivials are by definition far from random, but a lot of results say they are close to computable at the same time. And here's another, right? So if you're K-trivial, then you can't have a Martin-Löf random to compute 0 prime. If A and Z, the Martin-Löf random computes 0 prime, then Z already computes 0 prime. So in that sense, A is close to computable, right? What I did was translate incompleteness into some kind of downward closed property of phi Z1 plus, having density 0, relative to oracle one time and plane the other time. So the proof is not hard if you know the right things about K-trivials. ingenious, I would say, is the right word for this proof. Okay. So that was open for a long time and has been solved now using analytic notions. Right? Density 1 is still a mystery, though. Right? So density 1 point, of course, means having density 1 in every effectively closed set containing the real. So the question is, how much extra randomness do I need to get density 1 in every effectively closed set? I don't fully answer this. I have some partial results, though. For instance, balanced random is enough, right? And also, I tell you, it's closely connected to analysis, and in particular, differentiability of effective non-decreasing functions. So these came up in a different paper with Freya and Johansen and Stefan. So we defined a non-decreasing function to be interval RE if it vanishes at 0, and the difference f of q minus f of p is left RE uniformly in rationals p less than q. Right? So the differences, the displacements are uniformly left RE. Left RE means the things to the right, sorry, to the left of the real, my right. The things to the left of the real are RE, right? The left cut is RE. For continuous functions, this will imply lower semi-computable. So this is another weakening of computable, really. Markov computable was only take the computable reals, and here we just say the values aren't that computable. Right. This is closely connected to variation, defined in this way, the standard, the usual analytic variation, because here all these people together showed a continuous function is an interval RE just if it's the variation of a computable function. Right. So this is a natural class. Right to left is clear, but left to right needs a construction which in fact involves signed martingales. So we define the variation of signed martingales and show you get any left RE martingale out of that. That's with some conditions on top, right? So that shows hopefully that interval RE functions are an interesting and natural class, and you can now use them to gauge the deviation of Turing completeness for Martin-Löf randoms, right? The randomness enhancement principle says if you are Martin-Löf random, less computable means more random, right? So in this case, further away from 0 prime means more random, right? So therefore, these notions here will be connected to being further and further away from 0 prime and mean more random. Right? So you move down here and get more random. So the weakest notion I have so far is making interval RE functions differentiable. This implies being a density 1 point, which implies positive density, which is what I've told you already is difference random, right? The first implication is obtained by some calculation because, of course, the lower density is the lower derivative of the function measuring how much of the class I have up to x. So that lambda Lebesgue measure of 0x intersect p. The lower density is the lower derivative of this function, and 1 minus g in this case is 1 minus g is interval RE. Right? You can easily show that if g prime exists and z is in p, then it must be actually 1. It can't be less than 1 because then z wouldn't be random. Right? So therefore, this property implies density 1 point. This was too fast. The slides are on my website. So let's see here. Here's a notion we came up. Well, you'll never guess where, in Oberwolfach. So we wanted the number of changes to be very limited. In fact, the ways the components can change should be dependent on each other, right? So the idea is you have a monotonic Demuth test, meaning decreasing, and for any interval of stages, if Sm plus 1 changes twice, then SM also has to change, right? This means the opponent can't like sit down forever and save up changes of late components, right? He can't change the 1000th component a lot of times very late. That would be difficult. In that case, he would also have to change previous components, right? So the changes are the precious things he has, and he can't save them up too much, right? This weakens balanced randomness, which was studied previously. That's actually how we got there. Balance just means Sn, the version Sn can change at most 2 to the n times. Right? Balance because it balances the measure bound. Right? Oberwolfach is slightly stronger than Martin-Löf. Right? For instance, LR hard is a notion saying very close to Turing complete. It means every y random is random relative to 0 prime. LR hard things exist up here. So random things can exist up here still. Martin-Löf random, I mean. But they cannot be OW random. So that's the result. Did I say this right? No. Sorry, yeah. Other way around. If you're up there in Martin-Löf random, you are not Oberwolfach random. No. I should have taken a break. If you're Martin-Löf random but not more random, you are very close to computable. That's what it says. So yeah, okay. Yeah, this actually uses a different test notion. We have various test notions that are equivalent, and wasn't the original one. Right? You can be low in Martin-Löf random, not balanced random. Right? So if you say balanced, then you can get much. Sorry, if you only want to be not balanced, you can be much lower down. Right? So this shows balance is a proper subclass of Oberwolfach. Because this guy here will be Oberwolfach random, right? Otherwise it would be high up. Right? Okay, so what's all this good for? Well, one thing is they already imply differentiability of interval RE functions. So if you are random in this sense, then every interval RE function is differentiable at u, and in particular, your density 1 point. Any of these could have converses, but we don't know them at present. And now I can extend my diagram of Gaussian deviation by putting in OW random, and we know if it's not LR hard, then the thing must be OW random. Right? For all I know, all these could collapse, of course. I don't believe it. I mean, except for this. So we haven't separated these things, right? And we have looked at lowness notions for these classes in an attempt to separate them, found out each time it's K to reality except in the Oberwolfach case. Right? For difference randomness is actually due to Franklin and Ng, right? And for the interval RE functions, it's especially nice because the function class doesn't change, right? So interval RE is, for K to A, interval RE is the same as interval RE relative to A. So same holds for reals actually. So that's the proof we exploited. All right. So that gives the lowness, but for Oberwolfach we don't know it yet, right? So far it's a hypothetical notion, but even then it can be quite useful, right? We don't know what it is, right? But we have proved interesting things using it, right? Like some news on the covering problem. Right? So the covering problem is every K-trivial throwing below an incomplete random. So what we did was building a what one could call a smart k-trivial. It's pretty high up, and in particular, no y that computes it can be over Wolfach random, right? Which means it has to be high up. For instance, then it must be LR hard. Any y computing A must, and that's random, must be LR hard, right? The other result is if you have such a thing, it will compute every k-trivial, right? If you have a Martin-Löf random that's not over Wolfach random, it will compute every k-trivial. So one does it for all. That's what it says, right? So if covering is true, then I can fix that cover. There's a single thing computing all the k-trivials. Unlikely? I don't know. What's up there? That's the question. Okay, almost through. So I've told you how the variants of Demuth that get you very close to Martin-Löf are useful to analyze effective analysis, and to study lowness properties, right? The question remains in the last 3 minutes, how about the original notion? Is that now, can we forget about it, or is it actually still useful, right? So what does Demuth say about that? Is this notion still good? Answer, I'd say yes, right? You can use it to study extreme lowness, right? So consider a situation, y is random, A is below y, say RE, right? A is CE, y is random. And could share a proof for any delta 2 random there's such an A outside recursive. The idea now is the more random y, the lower A gets, right? So that's the way to study extreme lowness notions. Use some randomness notion that's still compatible with delta 2, and then A must be very, very low. Right. If y is just incomplete, A is already k-trivial, right? And so you can get inside k-trivial. One class is the strongly jumped traceables. So the idea here is that you have a C trace that captures that catches the values of the jump. The trace has an arbitrary order function bound. So you can, for any order function, you can pick such a trace. Kutcher and I proved that if y is Demuth random and A is below y, A is CE, then A is already strongly jump traceable. Right? So this principle works. Y is very random, A is very low. Great. In fact, we do this function-wise. So for each order function h, there's a test corresponding to it. Any A below y is h jump traceable. So putting all these together, if y is Demuth random, it passes all these tests, therefore it's fully strongly jump traceable. Right? The converse was proved by Greenberg and Turetsky. So if A is SJT and CE, then there's a Demuth random above. Right? So that's the Demuth SJT analog of the covering. It's true. Right? In fact, by recent results, you can even forget about CE here, because there's always a CE above. Right? So the full characterization is SJT is the same as below a Demuth random for C sets. One direction doesn't need it. Okay, so that's pleasing. Another notion is Demuth test compatibility. So there's no universal Demuth test. So for a fixed property, you could think of, well, for each test having an example passing that test, right? So that's Demuth test compatible for each E. Property E is compatible is for every test some Z with that property passes the test, right? So this big paper here, I used some methods and some others to show super lowness and super highness are Demuth test compatible. Super lowness down here means A prime is TT below 0 prime. Okay? And that gave a new, possibly simpler proof for C sets that if you are below all super low randoms, then you are strongly jump traceable. That's also true for super high, where you do need CE then. And my proof only works for CE, the new, recent proof. Right? So that works by considering these tests from the paper with Kuchera. So it comes out quickly using this property and the Demuth test compatibility. So that's pure recursion theoretic or lowness theoretic applications of the full notion, and the last one is inside SJT, right? So base for Demuth randomness means it's computed by something that's Demuth random in it. And these form a proper subclass, non-empty, I mean, not just computable, a proper interesting subclass of the strongly jumped traceables, right? So that's, we have arrived at the end. So I've shown you that the variants of Demuth are just the right thing if you want to be good for analysis, but still not compute the halting problem, right? The actual application of Demuth can be done with a much weaker notion, difference randomness. If you look at variance also close to Martin-Löf, then you get interesting interactions with analysis via porosity and density, right? And finally, the original notion is still great if you want to analyze extreme lowness properties. And just in time, I finished. There's some references. The paperback is out, as you've probably seen, and that's the general background, together with, of course, the book by Downey and Hirschfeld, Algorithmic Randomness and Complexity. And here's the papers referring to this talk selection. Thanks for your attention.
What's known about the Denjoy alternative for regular computable functions, not Markov?
Yeah, so that's the same as computably random. It's in the same text paper. So DA for usual computable function is the same as computably random. Some of this was proved by Demuth and the rest by us.
Other questions? I have one. So how robust are all this notion of randomness? For example, if we want to consider not reals, but points on a plane, or just points on a sphere, or if we want to make a computable permutation of digits in a sequence, which of them are robust and do not change? Since criteria are about the differentiability. For example, for two variables, it's not probably no more.
Okay, let's look some diagram. Also all are robust, and many are portable. So anything based on tests can be transferred to any computable measure space, right? And you, of course, you get invariants under things like computable matter preserving maps and stuff. So you get permutations of the bits won't matter. And extra robustness you get if you have a characterization by analysis, because then you also can show it's preserved under functions like taking the third root or so. Nice computable functions will also preserve the randomness.
But for example, just here, if we look at density 1 point in the plane, you get the same thing. Positive density also can be defined on the plane.
So this can be defined. This is actually on my list to study this in higher spaces. But the definition for the unit interval, for instance, didn't depend on the binary representation. It was an analytic definition, it's still here. So it's robust. And Turing incompleteness you don't really need, because there's the difference tests. So it's also robust. All these things are portable. The only non-robust candidates are things based on martingales. Jason will tell you more about this afternoon. So computably random is robust by Jason's results, and more or less, you see. But of course, in the unit interval, it is because you have the analytic characterizations by differentiability of non-decreasing computable functions. So the only critical ones are KL randomness and partial computable randomness, where I don't know even base invariance or anything else.
Okay, so thanks again.